Hello and welcome. Today we're looking at chapter 29, alternating currents. Firstly, we will look at the sinusoidal current and voltage, or the sinusoidal nature of current and voltage in alternating current. As we know that alternating current means that the voltage or the current alternates over time. Okay? There is a fixed period at which this alternates. For example, we in South Africa have electricity at 50 hertz. That means 50 times per second, or every 0.02 seconds, the current changes from the one way to the other way. Okay, so we can calculate this. This can be seen as a simple harmonic motion, which brings us back to the equations that we learned in chapter 20, 21, 19, I think 19, and where we said that the current at any given point of time, or the voltage, is equal to the maximum. So I0 is the maximum value of the current, the peak current, or V0, the peak voltage, sine omega t, or sine omega t. And we know that our omega is twice pi times the frequency, and the frequency, we know that the frequency is 1 over the period. So what you will do is you will start by taking the period of one oscillation, you calculate the frequency. Once you have the frequency, you can calculate, and you have the maximum value. Those are the two things you need. You need the period to get the frequency, to get the omega, okay? And you need the maximum value, and once you have that, you can calculate the current. Now we will look at the root mean square current and voltage. So thinking of any device, if you look at this, they give you a certain amount of power. This is a 20 watt lamp. Now guys, this is the average power, okay? And if we want to calculate the value of the average power, then we need to calculate in terms of P is V times I. But we have a problem, because if we think of our current and voltage graphs, okay, our average power, if we need to use our average current, our average is going to be 0, because half of the time it's this positive value and half of the time it's an equal negative value. So I can't say 0 times 0, because current and voltage will have the same problem. It gives me 20 volts. So we need to get a different way of calculating this. So to solve this problem, we go and calculate the root mean square current and the root mean square voltage. Now, what is the root mean square voltage and the root mean square current? As I've explained to some of you guys, that when we multiply power times is equal to voltage times current, okay? Because, let's say that's my voltage, let's say that's my current, okay? Because current and voltage are in phase, we're going to now have power, which becomes actually if we calculate the power, the power will always be positive, because negative times negative becomes positive. And we can see here that in the space where we get two waves, okay, we actually get one wave, we get two. So power is always positive, and also the power is half of the period. Okay, so the period of a power wave from there to there is in the space of half a current or an amplitude wave. So if we want to calculate the average power, okay, now these graphs are obviously not to scale, okay, because we want to work with the average power. Okay, we've looked at the average power. if we now ask how much DC current or voltage will give the same average power, okay, it ends up to be 70% of the I0 or the V0, the maximum current or the maximum voltage of the alternating. Okay, and therefore we use what we call the root mean square current. So how do we calculate this value? We know that P is I times V, but I can say that I squared over R as well. Now this allows my current that just goes to positive and negative. If I square my current value, which goes to positive and negative, I get a only positive graph. And if I take the average of that, this is my average. So this is an I squared graph. And this we would say is the average or the mean squared value. Okay, so if I take the mean squared value, okay, so that is a positive value, and I do the same for the voltage, okay, then I can go and calculate the power. So to get because we don't want the square value, we want the current here. So we calculate what we call the root mean square value. And we calculate the root mean square value for the voltage. And when we want to calculate average power, we multiply the root mean square value of voltage with the root mean square value of current. Okay, so what does this look like mathematically? We can calculate this value by simply saying that the root mean square current is the maximum current divided by the square root of 2. Okay, and that comes from this relationship that you do here, but you don't have to be able to prove this, you just need that equation. So you take your maximum value from your graph, you divide it by square root of 2, then you get your root mean square current. To get your root mean square voltage, you take your maximum voltage, divide it by the square root of 2, and then you take these two answers, multiply them together to get the average power. Okay, why would we want to use alternating current for electricity supply? The reason is that when we transfer electricity in wires, the more the current, the more energy is lost. So in DC, we can't lower the current and the voltage and change the current or the voltage, so that can't work. And we're going to look at how we do that just now. But in AC, we can lower the current, increase the voltage, transport it from one power station to the substations to the suburbs, and then lower the voltage again. And we're going to use the following method using a transformer. So transformers works as follows. Now if I look at this, I have a battery that has a current, and I've got another coil that has a lamp. If I move the two through each other, I get a current induced inside the lamp. Okay, I can increase that current by moving it faster. Okay, I can increase the loops, and that would also increase the size of the current that is induced and the voltage. I can increase the loops of the first one, which would also drastically improve it. But we don't want to make the coils go through each other the whole time. So what we can do is we can change our DC value into AC value, AC current. And now what happens is, as the current in the first coil changes the whole time, we have a changing magnetic field. This changing magnetic field makes the current in the second wire move. And by increasing or decreasing the amount of loops of the second one or the amount of loops of the first one, I can manipulate the size of the current and the voltage that I'm producing over here. So technically how it looks like this, where I've got two types of transformers. This is a step-down transformer. We've got coils on the one side and a single coil on the other side. Now what happens is we have a magnetic field that is induced inside the iron core. As the magnetic field changes every time the current changes direction, a new current is induced here. So what these two graphs are doing wrong is they're showing you that those two currents and voltages are exactly in phase. They're actually 90 degrees out of phase. So we step down our voltage by having more coils on the primary side and less coils on the secondary side, or we can do the following, okay, and we swap around the coils, and this is what we call a step up transformer. So here we have only a few coils on the primary side. The current induces a magnetic field. Every time the current changes, the magnetic field changes, and that changing magnetic field induces an alternating current on the other side. So this has to be alternating current. And by doing that, we can increase the voltage and decrease the current, or alternatively, increase the voltage and decrease the current. Okay. Since we have done this chapter before, we're just going to look at the formulas. Okay, where we'd say the voltage of the secondary over the voltage of the primary is equal to, and we use capital N for the number of coils in the secondary over the number of coils in the primary. So the same ratio of from secondary to primary in the voltage is the same ratio that the coils would have. So if I put 10 coils over 1, okay, that means my secondary voltage is going to be 10 times bigger than my primary voltage. If I put 1 coil in the secondary and 10 coils primary, that means that my primary voltage is going to be 10 times bigger than my secondary voltage. The other formula that we also use here, since it's important for us, we know that in a perfect system, the power in the primary is equal to the power in the secondary. So to get that, we take the voltage in the primary times the current in the primary, and that should be equal to the voltage in the secondary equal to times the current in the secondary. Now this is in the ideal transformer that does not heat up, and unfortunately transformers do heat up. So inside our metal core, okay, as the magnetic field flows there is a current being produced through this, and that current is called an eddy current. Now because, okay, how do you spell current? Because there's a current because it's a conductor, that current has a very, very high value, okay, of amperes, and that creates heat. Now this heat is energy that is lost from my secondary to my primary side. The next part we're going to look at is how to rectify and turn an AC current into DC. So with most of our household appliances, we have this problem that we use AC in the mains, but our device is DC. Okay, and when you charge your phone or something, you use AC current to change to DC current. Now we want to turn, and we call that rectify AC current into DC current. Okay, so if we think of our AC current graph, and obviously this goes for voltage as well. Okay, now if I connect from my AC supply, so let's say this is my AC supply, if I put a diode in there, okay, what's going to happen? The diode prevents any backward currents. So when I put a diode into my system, I get the following. I get a half rectified current. So it's going to be on, increasing, decreasing, off, increasing, decreasing, off, increasing, decreasing, off. So every half a cycle, so 25 times a second, 25 hertz, if it's a 50 hertz, we're going to have power. And that intermittent part is not going to work for our devices. That will break our devices, or it's not going to work as well. So what we do is we build a rectifier, and a rectifier looks as follows. So what we do is we use the alternating current, and we use the benefit that we have from diodes. So what happens is, as the current is flowing from the positive side, it can't go this side, so it flows here, and the object gets, the resistor gets its current, and then it flows back this way. Okay, and that's the loop. But if it alternates direction and it goes this way, it can't go in there, so it goes here, it goes that way, and it can't go this way, so it goes that way, and it goes back. So we effectively, by using two opposite diodes, we effectively turn our negative negative current into positive. So every time we had a negative, we have now turned it into positive. Now we still don't have a DC current, an equal consistent current. So what we want to do is we want to add another component to rectify and to smooth. We've rectified, now we want to make it smooth, and to do that we put a capacitor in here. Now putting a capacitor in here allows for every time that the current goes down, it doesn't go down all the way, because the capacitor in those split seconds gives off some of its energy. It stores charge, and the moment it goes zero, maximum zero, the moment it goes to zero, the capacitor kicks in, and then the capacitor also gives energy. So what we have is we end up with this. So we end up with a graph that is almost a straight line. Now in the textbook you will see this much clearer. So by rectifying and smoothing it, we almost get a perfectly correct line that is almost perfectly DC. I hope this has some clarity for you guys, and if you have any further questions, please don't hesitate to ask. Have a nice day. Goodbye.